In the next few minutes, I'll show you what a large language model actually is, how it learns, why it thinks in tokens, what the scale race is really about, what these models can't do, and how to reason about the differences between GPT, Claude, Gemini, and Llama. Welcome to Concept Stack. We produce one concept a day, and each one stacks on the last, building the framework for AI together. Let's dive into LLMs. Here's the whole trick, stripped down. A large language model takes a sequence of text and predicts what's most likely to come next. That's it. Give it the words, quote, "the cat sat on the," unquote, and it outputs a probability distribution across every possible next word. Mat, 62%, floor, 14%, chair, 9%. It picks one, adds it to the sequence, predicts again. That's how an LLM writes essays, answers questions, debugs code. One token at a time, each one the most likely continuation of what came before. There's no understanding in there, in the conscious sense. There's a very, very good next word guesser, trained on enough text that the guesses look like reasoning. The jump from guessing next words to drafting a legal contract isn't magic. It's scale. How does a model learn to guess next words well enough to be useful? 3 phases, each more carefully curated than the last. Phase 1, pre-training. The model reads trillions of tokens of raw text. Books, Wikipedia, most of the public internet. For every passage, it predicts the next token, gets told what the real next token was, and adjusts itself to be less wrong. Do this for billions of passages, and it learns grammar, facts, patterns, styles. Phase 2, supervised fine-tuning. Now the model sees carefully written prompt and response pairs. Humans wrote both sides. The model learns what a helpful answer looks like versus just a statistically likely continuation. Phase 3, RLHF. Reinforcement learning from human feedback. The model produces several responses. Humans rank them from best to worst. The model learns to prefer outputs humans like. This is how you get from a raw next token predictor to something that says, "I can't help with that," when it shouldn't. Models don't read words, they don't read letters, they read tokens. A token is a subword chunk, usually somewhere between one character and one short word. The word unbelievable gets split into 4 tokens. Able, plus the exclamation point. Each token maps to a fixed numeric ID in the model's vocabulary. The model only ever sees those IDs. Common English words are often 1 token each. Rare words, code, foreign languages, those fragment into many tokens. A single emoji can take 4. This matters for 3 reasons. 1. Tokens are the unit of cost. API pricing is per million tokens in and out. 2. Tokens are the unit of context. When you hear a model has a 200,000 token context window, that's how much text it can hold in memory at once. 3. The choice of tokenizer shapes what a model is good at. A model trained with an English-heavy tokenizer chews through French text 4 times slower because French fragments into more tokens. A model's size is usually reported in parameters. A parameter is a single numeric weight inside the neural network, and a model's intelligence, very roughly, scales with how many of them it has. In 2019, GPT-2 was considered huge at 1.5 billion parameters. By 2020, GPT-3 was 175 billion, 100 times bigger, and the first model that felt like it could do a wide range of tasks zero-shot without specific training. GPT-4 and Claude are thought to be well into the trillions, though the exact numbers aren't public. Llama 3, Meta's open model, is 405 billion parameters and freely downloadable. More parameters is not strictly better anymore. In the last 2 years, the frontier has shifted towards smarter architectures, longer context windows, better fine-tuning, and built-in tool use. A 300 billion parameter model from 2024 outperforms a 500 billion model from 2022 on almost any benchmark. Here's where a lot of people get lost. A model doesn't hand back a single answer. It hands back a probability cloud, every possible next token ranked by how likely each one is. Something still has to pick one. That step, turning the cloud into a specific chosen word, is called sampling. And the knob that controls how much randomness goes into sampling is called temperature. Why does temperature matter to you practically? Because the same prompt at different temperatures can produce a working product or a broken one. Temperature 0 means always pick the single most likely token. Deterministic, same input, same output, every single time. This is what you want when you're extracting fields from an invoice, generating code, translating between languages, or answering a factual question. You don't want variety. You want the single best answer. Temperature 0.7 is the default for conversational models. A little randomness makes answers feel natural, not robotic. ChatGPT and Claude both default around here. Use it for chatbots, support, general Q&A. Push past 1.0, say 1.2, and the model starts picking less obvious tokens. More interesting metaphors, more variety between runs, also more hallucinations. This is where you live when you're brainstorming product names, writing fiction, or trying to make the model surprise you. Rule of thumb: if the output has to be verifiable or consistent, start at 0 and nudge up only if the result feels too stiff. If the output is meant to be creative, start at 0.8 and nudge from there. Temperature is one of the most important knobs you'll ever touch, and the one most newcomers leave untouched at the default, even when it's wrong for the task. There are 4 things these models are famously bad at. Knowing all 4 saves you a lot of frustration, and in production, a lot of bugs. Let's take them one at a time. 1. Arithmetic. A model that can explain the quadratic formula can also get 84 times 17 wrong, and state the wrong answer with complete confidence. It isn't computing, it's predicting what the next digit usually looks like. Give the model a calculator as a tool, and the problem disappears. Make it reason in its head, past 3 or 4 digits, and you'll catch arithmetic errors in production. Don't let a language model do your math. 2. Knowledge past the training cutoff. Every model was trained on a snapshot of the internet taken at some point in the past. A model whose cutoff was mid-2024 does not know about events in 2025. It does not know the library version you're using or the API that shipped this morning. Worse, it usually won't tell you it doesn't know. It will guess in detail and with confidence. That's how you end up with hallucinated function signatures and invented release notes. Fix: give the model a web search tool or paste fresh documentation directly into the prompt. 3. Persistent memory. Every conversation starts from 0. The model does not remember who you are, what you worked on last week, or that you already told it about your project structure an hour ago. Products like Claude and ChatGPT add a memory layer on top of the raw model, but the model itself is stateless. It sees only what is in the current context window. Anything you want it to remember, you either resend every time or use the host's explicit memory feature. 4. Self-awareness about what it knows. This is the hardest failure to catch because the output looks identical to correct output. A model will confidently cite a peer-reviewed study that does not exist, inventing the journal, the volume, the page numbers, and the author names in matching formatting. The technical term is hallucination, and every major model does it at varying rates. The only reliable defense is to verify anything authoritative sounding the model tells you. Citations, statistics, API signatures, legal references, always check. 4 families you'll hear about constantly. OpenAI's GPT line, currently the biggest mindshare, runs behind ChatGPT and is available via the OpenAI API, strong at general reasoning, the default people reach for. Anthropic's Claude, the family from the lab that also publishes the most detailed safety research, known for very long context windows, strong coding and analytical writing, and a carefully calibrated refusal to help pattern when asked to do something risky. Google's Gemini, the one deeply integrated with Google Search, Android, and the rest of their stack. Multimodal from the ground up, it handles images and video natively, not just text. Meta's Llama, the open weights family. You can download the model file, run it on your own hardware, and fine-tune it for your own use case. Most of the open-source AI ecosystem is built on top of Llama or one of its derivatives. You don't pick one and stick with it. You pick the one whose trade-offs match the task in front of you. It's easy to dismiss these models as autocomplete on steroids, and in a literal sense, that's what they are. But autocomplete on enough data, with enough parameters, turns into something strange. A single model with no task-specific training can draft a contract, debug a regex, translate Japanese poetry, and explain a research paper. That kind of general-purpose text interface did not exist 5 years ago. It barely existed 3 years ago. Every concept in the rest of this series, tokens, embeddings, RAG, agents, MCP, tool use, is downstream of this one idea. An enormous trained model that predicts what comes next, given what's already there. Get this foundation right, and the rest of the stack becomes legible. That's the end of this concept, but each video stacks on the last. Subscribe and we add the next layer tomorrow. New videos every day on the AI concepts you keep hearing, but nobody defines cleanly. Tomorrow, what is a token? The unit that models actually see, and the unit that your API bill is denominated in. Thanks for watching.